Good afternoon, everybody. Thank you for joining us for today's PowerTalk webinar hosted by A&A. Today's webinar will be going over battery technology deep dive. And the speaker today is Michael Yin, who is A&A's VP of Product Engineering. Michael is an innovative product development and engineering leader with 20 plus years of experience driving product realization, design engineering, and technology management. He's skilled in building product business and financial cases, leading cross-functional teams and guiding projects from concept to commercialization. So we'll have Michael speak for about 30 minutes and then there'll be time for questions at the end. So if you have any questions, please put them in the chat or use the Q&A feature. So Michael, get started whenever you're ready.
Thanks, Catherine. Hi, everyone. My name is Michael Yin. I'm the VP of Engineering here at A&A. I'd like to thank all the attendees here for joining, and I want to thank EGSA for hosting this webinar and allowing us the opportunity to share our knowledge and our expertise. At A&A, we provide mobile power to the construction industry and adjacent industries. We provide mobile compressors, diesel generators, power modules, which are energy storage systems, and hybrid energy systems, which combine our generators with with our power modules. Today, I'll be talking about battery technologies and hybrid energy systems. In this presentation, we're going to be talking about the following topics: battery history, how a battery works, battery characteristics, fire risks, battery temperature performance, battery cycle life, power and energy density, automotive examples, how hybrid works, and why hybrids. Now, we want to look into the automotive industry to see how they've transitioned from internal combustion to hybrid and EV offerings. We want to see how they've utilized battery technologies to make the most efficient vehicles possible and see how we could apply that to our industry, which is power generation. Let's quickly look at battery history. Batteries have been around for about 2 centuries now. The first lithium battery was developed in the 70s, and commercially, the first rechargeable lithium battery was commercialized by Sony in 1991. So we started seeing electric vehicles in the 2000s, and now there are so many chemistries. We're only going to talk about the most popular and most commercialized ones today. Also talk about an up-and-coming chemistry. You probably heard it all over the news recently, which is a sodium ion. With most chemistries, we are super reliant on rare earth minerals, and we're seeing more and more investment these days into research and utilizing more readily available materials that don't rely as heavily on mining and refining. Here's the basic idea of how a battery works. In a nutshell, a battery stores chemical energy and converts it into electrical energy through a series of electrochemical reactions. All batteries have an anode and a cathode current collector at both ends. They're usually made of copper on the anode side for conductivity and aluminum on the cathode side to resist oxidation. There are other materials being used to replace these that better resist dendrite and corrosion formation that degrades and reduces the cycle life. The electrolyte is a liquid that dissolves and ionizes the salt, in this case lithium, and creates lithium ions. In between, you have a thin separator film, usually made out of polypropylene or polyethylene, that allows ions to flow freely back and forth through the electrolyte. So the left illustration shows a charging scenario for a lithium battery, and the right shows a discharging scenario. The lithium ions are moving back and forth through the electrolyte, and electrons flow through an external circuit outside the battery. There are tons of illustrations and videos online that can provide additional details, but this is generally how energy is stored and transferred through. Key battery characteristics. There are many different battery chemistries available. There's no such thing as the perfect battery. There are positives and negatives to every single chemistry. Batteries are designed to prioritize certain characteristics that are important to the application. As designers and integrators, we get to select which characteristics are most important to our application. Here's an illustration showing six key battery characteristics. You have safety, such as overcharging, puncture, or impact resistance, and what happens during thermal runaway. Power density, this is the watts per kilogram. This is how quickly a battery can deliver energy. Energy density, this is watt hours per kilogram or sometimes watt hours per liter. This is how much total energy the battery can store. You have the cost, which is the initial cost or the capital cost, as well as the operating costs and overall efficiency of the system. You have lifespan. This is the number of cycles at whatever depth of discharge. This is the total capacity and useful life of the battery. And you have the temperature range. This is the performance at room temperature versus cold versus extremely warm conditions. When designing a hybrid energy system and selecting a battery chemistry, we need to ask ourselves what characteristics are most important. Well, that really depends on your goals for the application. Out of these six characteristics, we can all agree that safety is probably the most important consideration. If a chemistry is not safe, we should probably rule it out. Fire risk by battery chemistry. Let's talk about safety in terms of a fire risk. Here are a handful of available battery chemistries. I know there are many other chemistries not mentioned on this list, but most of these chemistries have had some commercial success. As I mentioned, safety ought to be the highest priority, if not the top priority. So many of these riskier chemistries, such as LCO, lithium cobalt, for example, would not make a great option if you were to build a hybrid system today. The safest option available is currently LTO, followed by sodium, and then LFP in terms of the lowest risk for fire and thermal stability. Some chemistries, if they do go into thermal runaway, react very violently to water. So it becomes very challenging if a fire does occur. I think most fire agencies will just let the batteries burn out. That said, the that said, I believe the LTO is the only chemistry on this list that can be extinguished with water. You'll see NMC used in hybrid energy systems, and you can design in safety, such as fire suppression, and still have a very safe system, like they do with EVs today. But if you were to build a system today, there are safer options, unless weight and energy density is one of your top priorities. Now, let's look at the next important characteristic, which is temperature performance. We're only going to look at the three safest chemistries here, LTO, sodium, and LFP, for the sake of this comparison. So battery temperature performance. In terms of overall temperature performance, the top performer here is LTO, then sodium, and then LFP. I'm not presenting, like I said, information on the other chemistries since these three are the ones we should consider most if we were to build a hybrid system today. I'm not saying other chemistries are bad. It's just that these chemistries in our power generation industry is what we would consider today if we were to design a system. One important temperature performance consideration is the charging rates at extremely cold or extremely hot conditions. Testing is very important, and you have to look beyond what the marketing material says. For example, sodium here in this chart looks almost as good as LTO, and it says that it could charge at minus 20 Celsius. But that's a little bit misleading because its charge rates actually slow down to about 1/10 of a C when it gets that cold. You have to get it up to temperature to, maybe 10 degrees Celsius or so before you could hit it at a full C or 2C charge rate. This is why you can't go by the headline specs alone. You have to really dig in and test it yourself. The devil is in the details here. Now, extreme hot or extreme cold conditions can be overcome with heaters and cooling. This does add to the system and pack costs and will affect overall system efficiency. Batteries should be used to run your load, not not heat or cool down your batteries. Otherwise, you end up wasting energy. The clear winner here is LTO, but all three chemistries are viable and can be used effectively if designed correctly. Now, let's look at another important battery characteristic, which is lifespan or cycle life. So, battery lifespan and cycle life. I mentioned that the devil is in the details. This is where the most confusion occurs. Battery cell manufacturers tend to be a bit optimistic when it comes to cycle life. You'll see huge cycle numbers, but you need to look at the depth of discharge to understand the total lifespan of the battery. To make things simple for this theoretical case, let's look at the depth of discharge at 100% to put them all in a equal playing field. Let's look at the three chemistries, LTOs, LTO, sodium, and LFP. Now, you'll see that LTO has 20,000 cycles at 100% depth of discharge. Uh, that means for a 50 kilowatt hour pack, you have basically a gigawatt hour of capacity. Um, you know, uh, Currently the cost is quite high. It's very high for LTO. So a 50 kilowatt hour pack at $1,000 per kilowatt hour, that's $50,000 for the pack. If you look at the lifespan costs, so you multiply the number of cycles, 20,000 cycles by 50 kilowatt hours, you get about 0.05 kilowatt hours. Uh, that's the overall lifespan cost per for the power. Um, if we look at this case for 3 cycles a day on this 50 kilowatt hour pack, that's 18.2 years that this 50 kilowatt hour pack will last you. If you look into sodium, I have sodium twice here. I have a sodium Gen 2 and a sodium Gen 3. So sodium have really become more commercialized basically in 2021. Let's call that Gen 1 sodium. Back then, sodium had a cycle life of about 1,000 cycles. They were not very energy dense at all. They were quite heavy. We would call that Gen 1. Gen 2 sodium, this is like sodium that we have today, 2024, 2025. That's about 3,000 cycles. Um, Energy density not quite as high as LFP, but getting there. And then we have sodium Gen 3. This is the sodium. If you check the news, this is what they're talking about. This is 10,000 cycles, okay? 10,000 cycles, and they're expecting the cost to be even lower than LFP sometime in the future. Could be 5 years, could be 3 years, we don't know, but that's of sodium Gen 3. We're going to start seeing Gen 3 sodium in 2026. Um, so here we also have LFP, which is 3,000 cycles at 100% depth of discharge. Of course, when you have a lower depth of discharge, like 60%, then you see LFP go as high as 5,000 to even 10,000. So here, in terms of cost, you have in terms of lifespan cost, LTO is actually just 5 cents, and the other chemistries are actually a little bit more expensive. But sodium Gen 3 is actually going to be the cheapest. But of course, that technology is not available yet. So we should take that with a grain of salt, right? For sodium Gen 3, because that's not quite there yet. So in this chart, we're going to look at the battery lifespan and cost for an application where you need this system to run for 10 years. So if you need a system to run for 10 years, that 50 kilowatt hour LTO pack, I think it said 18 years on the previous slide. So if you only need it to last 10 years, that means your battery pack needs to be only 27.4 kilowatt hours, okay? So that means you're going to be cycling it about 5.5 times a day. Therefore, your total pack cost for this 27 kilowatt hour pack is going to be about $27,000, okay? For sodium, because it's 3,000 cycles, you're going to need 182 kilowatt hour pack. At $250 per kilowatt hour, that's 45,000. And for LFP, which has the same number of cycles, 3,000 cycles, that pack is going to cost you about 36,000 at a cost of $200 per kilowatt hour. Sodium Gen 3, because it has 10,000 cycles, you only need a 54 kilowatt hour pack. So that's only going to cost 13,000. So in the future, sodium will be the cheapest. But currently, right now, if you look at the battery packs, LTO is the least expensive option. Now let's look at the actual battery lifespan it costs. So for this application, many of you are going to say you would never use a battery at 100% depth of discharge. You would only use a much smaller depth of discharge. So here for LTO, we're only going to use 80%. Same thing with sodium. And for LFP, we're going to use 60% depth of discharge. So with these lower depths of discharge, you have greater cycles. For LTO, you're going to have about 80,000 cycles. And for sodium, second gen sodium, you're going to have 10,000 cycles. Same thing with LFP. You're going to have a really good LFP cell will get you 10,000 cycles at 60%. And third gen sodium, you're going to have about 25,000 cycles at 80% depth of discharge. So you also have to take that number with a grain of salt. That is the cycle life at 25 degrees. Now we know that in actual applications, it's very difficult to maintain that temperature. So let's assume that everything's at 40 degrees. So in an actual use case, let's assume these batteries that are at 40 degrees. So let's cut those numbers in half. So 40,000 for LTO, 5,000 for sodium and LFP, and 12,500 for sodium third gen. So if that's the case, then the life cycle capacity is what's displayed there. 876, 730, and about 547 for both LFP and third gen sodium. Power and energy density. In terms of power density, LTO has the highest density, followed by sodium and LFP. For energy density, LTO has the lowest, and LFP is currently the highest. But third gen sodium is very similar. Of course, NMC is the highest, but it's not displayed here because if we were building a system from scratch today, we probably wouldn't select NMC. This is important for hybrids if your application is mobile. Energy density and power density might not be as important if it's a stationary application. Automotive hybrid examples. So early on, I talked about the automotive industry and how we can learn from it. Here we have the most fuel efficient hybrid vehicles available. We have the F-150, Honda Civic, Accord Hybrid, Sonata, and Santa Fe hybrids. And you could see the gas engine miles per gallon. And you could see the difference between the gas models and their hybrid models. There's a significant difference there, right? And here on the right, you'll see the battery size. So they're using a very small battery, and they're cycling it quite a bit. Many of them are using some sort of LFP chemistry, and you can see here that these automotive manufacturers are able to squeeze out the most miles per gallon possible using a very small amount of batteries. By doing this, they're able to make their vehicles more cost effective, and now they've become 100% mainstream. So when we're looking into hybrid energy systems, if we want them to be mainstream and we want them to be used more frequently and more common in our industry, we need to look to this model to see how can we make these systems as cost effective as possible to achieve the greatest result, right? If we're able to do that and also be economical, then these hybrid energy systems will become very standard and could potentially take over. So how do hybrids work? So you saw in the previous slide that hybrids make cars more efficient. Well, a hybrid makes a generator more efficient. It does that by running that generator at a very optimal load, at a higher load where it's very efficient in terms of kilowatt hours per gallon of fuel consumed. Okay. When you lightly load a generator, it becomes very inefficient. But when you're heavily loading it, it becomes very efficient. And what you want to do is you want to store that energy. You want to run that generator when it's nice and efficient, and you want to store that energy into the batteries. And then you want to, if you can, you want to be able to turn off the generator and run that load off of the batteries. There could be some incidences or some cases where you have a higher load, and if that's the case, then you want to run that generator continuously if you can, because that generator is already at its optimal efficient condition when it's at that higher load. So a hybrid energy system will determine your load and figure out, hey, do I need to run a generator or should I cycle the batteries? So that's basically how a hybrid energy system works. And you could achieve some great results using a system like this. If your application has cases where the loads are variable, then this application makes a ton of sense. Hybrid system components. These are some of the components in a hybrid energy system. If your system needs to be mobile or portable, we need to look at the six characteristics and see what characteristics are most important for the application. Here in this mobile application, you have a generator on board that has about a 200-gallon fuel tank. If 1 gallon of diesel can provide about 12 kilowatt hours of stored energy, that means that 200 gallons of diesel on board is equivalent to about 2.4 megawatt hours of energy. So when we look at the six characteristics, safety, cost, energy or power density, temperature, performance, and lifespan, let's see what's important in this particular application. Here, this product is mobile, so weight is a factor, but at the same time, because you have fuel on board, you don't need a massive battery because, as I mentioned, 200 gallons of diesel get you about 2.4 megawatt hours of energy. Okay, so here, power density is important because if you could get away with less batteries, then you could cycle it more. Now, if you have an application where, let's say, for example, it's an event and you cannot have that generator run at all, then you would need a battery with a higher energy density. So, for example, LFP or NMC, right? That ways you could run this hybrid system continuously for very long periods of time without the generator coming on. Now, when you are charging it, that generator will has to come on and charge that much larger battery. So when you look at the total cycle life of that generator, or how many hours you have to put on it, energy is energy, right? So that generator still has to run the same amount of time. It's just the number of cycles that it's on and off. Okay. So here, you need to factor in cost, energy density, temperature performance, right? If this is going into an application in California or where it's very moderate, you don't need to worry about temperature performance that much. But if this has to operate in extreme cold conditions or extreme hot conditions, then you need to consider keeping those batteries at a certain temperature, right? If we were to use an LFP battery, for example, in extremely hot or extremely cold conditions, yeah, you would have to install heaters or HVAC, and that would cause this system to be significantly larger. And if it gets to a certain size, it gets to a point where you can't necessarily trailerize it anymore. So it loses its mobility. So that's why I said it's really up to the application. The battery technology you select really depends on the application. Here is a 1 year independent case study that we've done with one of our customers. So it's a hybrid use application. It's a pretty unusual case where this is a 25 kVA hybrid generator is being used to power a guard shack for a whole year. In this particular application, it's running 24 hours a day. Loads were pretty low. They're typically under 1 kW for the most part. Of course, there's starting loads, and at night sometimes they'll run lights and things like that. but it's a pretty lightly loaded application where they would normally put a 25 kVA generator. Here, by replacing with hybrid system, the fuel efficiency increased dramatically. Um, we saw 83% reduction in fuel burn versus a standard generator. And in this case, the generator ran only 783 hours. So that means during the time it was deployed, the customer only did one oil change. In an entire year, they only did one oil change at the 500-hour mark for this application. Our customer told us that uh, the financial impact was about $15,000 a year of operational savings in fuel and maintenance costs. So this is a great application where lightly loaded or variable loaded application where a hybrid makes a ton of sense. So the conclusion why we want to go with hybrids, well, it reduces fuel costs, as mentioned in the previous slide. It reduces maintenance. Uh, Service people are hard to come by. So if you're able to reduce uh, the service intervals from every 3 weeks to every 2 or 3 months, that's a huge improvement. Longer generator life because you're running the generator less. This asset becomes a much longer useful asset for you. Increased efficiency. You're making the most out of the fuel that you have, right? So you're burning that fuel most efficiently with that generator, and you're storing that power. Your total cost of ownership could be lower over time. Of course, there's a higher initial cost or capital cost, but if you look at the overall life of the product, you should get a return on investment in about a year or two if you're running it 24/7. Emissions compliance. These generators are used in a hybrid application are going to be much cleaner than any tier 4 or future stage 5 generator that requirement in the future. Remote monitoring. A lot of these hybrid systems do have telematics on board. These systems have the ability to report on your fuel savings, your emission savings, so that you could report on that. Overall, a better user experience. You're not going to have wet stacking if you're using a diesel generator anymore. Much quieter and reduced overall carbon footprint. Instead of going through 2 or 3 generators in 10 years, you could get away with one generator, one hybrid system, and that single generator could last you the entire 10 years. So it's an overall better experience and reduced carbon footprint. All right. Thank you very much for watching. Let's go ahead and open it up for questions.
All right, thank you, Michael. So we have a couple questions. First, just a general question. Will attendees be able to get a copy of the slides from the presentation?
Yeah, that's definitely possible. If we have
Okay.
your information, we could definitely send that over.
Yes, I'll make sure you have it. Okay, next question. For the data center industry, the LMO/NMC chemistry is by far the most deployed by Li-ion battery. Are sodium-ion battery comparisons to the LMO/NMC chemistry available?
Yeah, so I when you look at Tesla for their systems, I think they switched over from NMC batteries to LFP batteries in about 2021, 2022. That's when you started seeing them switch over. Um, uh, for those applications, if you have the real estate, if you have the space, I could definitely see switching eventually over to sodium. It's a safer and much more cost-effective battery in the future. Maybe not today, but definitely in the future. Um, I definitely see them switching over soon. Newer data centers, I see them using less and less NMC and more LFP, just because of the cost and the cycle life, a little bit higher with LFP. So we'll see where it goes in the future. But right now, I really think sodium is going to be the future, and that's what all the reports that we're seeing in the news and things like that, we see sodium really making a big impact in the future.
All right, thank you. And then, next question, why should I use a hybrid over a standard generator?
So this question really depends on your load. If you typically have a pretty stable load, or a reasonably high load, medium to high load, it does make a lot more sense to use a standard generator. We're talking about for a mobile application or off grid, right? Um, but if you have variable loads or you have cases where it's very lightly loaded, then it does make sense to use a hybrid system where you're able to store that energy when you are lightly loaded. And when you are heavily loaded, then that hybrid system could definitely run that generator continuously during those times.
Okay, and then kind of going along with that, so when doesn't a hybrid make sense? What applications?
Right. So those much higher loaded applications, uh, generators are very efficient above, 50, 60%, 60 to 80%. They're extremely efficient. So when you have loads that are that high, it's best to run the generator continuously at that point. It doesn't make sense to charge batteries and cycle necessarily when that generator is running at that high of a load. And it's if you look at fuel curves of these generators, they're very efficient, typically above 60%. That they're close to optimal efficiency, 60 to 90%, sometimes higher.
Okay, and then how easy is it to parallel these units together?
So it really depends. There's a couple different systems that are available. I could speak for the ANA system. We use a Droop style paralleling system where we basically run one of our power modules, and then the secondary power module is able to parallel with that power module at the bus. So there's no other controls needed. It's able to parallel quite simply that way. There are isochronous controls for other systems that are available that are able to parallel to the grid. But for our systems, we've designed ours to parallel a slightly different way to just simplify it for our customers. Our customers are able to parallel our systems a little bit differently than other systems.
Okay, that's all the questions so far. Is there any one? Okay, what got your company into the hybrid energy industry?
Oh, so that's a funny story. So, when I joined the company about 5 years ago, I was working on a product called a smart load. We had an issue with diesel generators where our diesel generators, Tier 4 final diesel generators, would wet stack. And it was always a service nightmare. Generators would shut down randomly when they are wet stacked. Because in our industry, our construction industry, we have to like variable loads all the time, right? If you think about construction equipment like cranes, construction elevators, pumps, things like that, those are variable loads. And after a large transient load is usually a pretty low load afterwards. So wet stacking has always been a big issue with Tier 4 final engines. So I developed a smart load and which has a built-in load bank on the generator. It basically applies about a 40% load when you're lightly loaded on that generator. So it's like a dummy load. And we were wasting a ton of fuel with that product. So we decided, we could store that energy into batteries instead. That'd be a much better use of that energy and that fuel. So we decided to develop hybrid energy systems, much better on the environment and more economical as well because you're burning less fuel and you're able to shut that generator down, putting reduced hours on that generator and reduced maintenance.
Okay. And, uh, we've seen a significant battery pricing increase post-COVID, accentuated by pressure from data centers. Are the life cycle cost numbers based on recent prices?
Yes, so those prices were just some prices I found. I don't know if they're the very latest, but it's the packaged price. So that includes cooling. It's the packaged price, right? Sale price is definitely much lower, right? You see LFP reaching as low as $50 per kilowatt hour, and there are reports for sodium going. There could be some optimistic reports, but they're saying sodium could go as low as $20 per kilowatt hour in 5 years, right? Um, but um, but yeah, we are seeing price increases post COVID, and of course with tariffs. So as a result, I think we need to figure out if we're able to get away with a battery chemistry that gives you more cycles for the same dollar amount. I think we need to look into that direction moving forward.
Okay. What would you consider the best battery chemistry and why?
This is a tough question because it really depends on your application. I mentioned if you're trying to get maximum range in an EV, for example, you probably want to go with NMC battery or possibly a solid state battery in the future because of the lightweight. But for energy storage, um, you want energy storage to last a long time. You want it to last, at least 10 years, right? So you definitely need a cycle life to handle that. Ideally, you'd want a chemistry that doesn't rely on temperature control too much, because if you have to run heaters and coolers, HVAC systems and things like that to keep the batteries, at a moderate temperature, you're just wasting power and you'll end up cycling the battery more. So if you could get away with a battery that doesn't require that, that would be ideal. Right now, if I was to, right now, LFP is a great option. OTO is a good option for certain applications, especially for mobile applications, which is what we do. But, if you're focused on data centers, something stationary, then I would say right now I would go with an LFP or a sodium battery. Give sodium battery a little bit more time. It's still got a long way to go before it could reach cost parity. With LFP, it's still more expensive today, and it's probably going to be more expensive next year, but it does have some benefits, some great benefits. I mentioned take it with a grain of salt because it's still relatively new. We're in what I call our third generation of sodium coming out next year, and we're going to see some improvements very soon. A few big players in there are CATL. Uh, if you look in the news, they're coming out with a what I call a third gen sodium battery in December of this year. And December of this year, that's when they're launching it. And their intent is to use that in a lot of their automotive applications.
Right. And hybrid sources fare in terms of bus stiffness in high and rush applications.
So high inrush applications, it really depends on the battery chemistry, but certain chemistries like LF, LTO, for example, it could handle very high inrush. I think I've seen up to 10C. I know that for LTO, it could handle up to 4C without any active cooling or active heating needed. It can handle up to 4C. Sodium could handle quite some inrush as well. Um, you're starting to see quite a bit of sodium used today. You see a lot of cylindrical cells being used today in automotive batteries. Batteries, a lot of lead acid batteries in your car today, if it's really hot, uh, here at ANA, we're based in Henderson, which is south of Las Vegas. And here, the batteries don't last more than 2 years here because of the heat, right? If you use a sodium battery, you could actually get away with fewer cells. So I've seen a pack of sodium batteries in an automotive application where there's only like four or six cylindrical cells, and the rest is empty space because it could handle like 10C discharges. So it's a great application for things like that.
Okay. And where do you see battery technology in 5 years or 10 years?
Oh gosh, this is the crystal ball, right? So hopefully solid state comes to existence. Y- I have a buddy who has a solid state kind of like a brick charger t type deal that he purchased. Right now, it doesn't have a ton of cycles, but it is very light. It is very energy dense, but it doesn't have a ton of cycles right now. Hopefully, that technology improves. I see sodium and other types of technologies that require less mining, less of those rare earth minerals and things like that, right? So if we could come up with those types of alternatives where we're less reliant on global global issues and things like that, I really see that type of battery technology moving forward, where we're able to produce some of it here in the States.
Okay. What would this hybrid systems be certified to? What are the code requirements?
So it really depends on the application. For a lot of mobile applications, there are fewer certifications. But for stationary, they're definitely higher. There's just all sorts of different certifications for safety. You know, you have 1741, you have 9540, just to name a few. We actually have a great webinar that one of my colleagues, Kevin Speech, presented, where he actually goes into details there. We could possibly send you a link to that presentation where he goes into a little bit more details about some of those UO and safety requirements.
All right. And how long will typical energy storage battery last? How do you dispose of energy storage batteries?
Hopefully, you're designing it to last at least 10 years, possibly longer. You definitely want to select a battery that can handle the cycles and the size to meet your application. But ideally, you'd want it to last over 10 years. Otherwise, and you're also going to need to look at your ROI. There's a lot of calculations that need to be figured out in order to determine all that stuff. Um, what do you do with the batteries? How do you dispose of them? There are recycling programs. Currently, they are quite expensive to get the lithium out of the batteries, so it is quite expensive. Other chemistries like sodium, you probably would not be recycling those type of batteries. There could be some, there's a little bit of aluminum in there, but a lot of it's carbon, for example, for sodium. So those uh, some of those components are not really worth a lot of money, and you can scrap them safely because they are super abundant. So yeah, recycling programs right now not super cost effective, but they are getting there.
EBOS can you parallel, or how many have you paralleled?
Uh, so our eBOS, we have paralleled, I think, about 64 of them. We don't have a number because technically you could parallel an infinite number of units together. So they are used as kind of a building block to build your power system. So I've seen 64. It could definitely go much higher. There really is no limitation to it right now.
Does the battery wet stacking when doing regular services?
Pardon, you're breaking up a little bit.
Sorry. Does the battery load help prevent wet stacking when doing regular services?
Absolutely. So when you run a hybrid energy system, you're running that generator at a high load. So when it is running, it's running at anywhere from a 75 to, 60 to 90% load on that generator. And what that does is it allows it to run at its peak optimal operating temperature. And that just eliminates wet stacking from even happening. So you could discard your load banks. You really don't need it anymore when you're running a hybrid system.
Um, okay. Why do most energy storage companies use LFP?
It's definitely a great option because the cost is quite low right now. So a lot of money has been put into LFP. Um, so it's definitely a great option, especially if you're looking for a high kilowatt hours, right? If you have an application that requires that. There are some drawbacks with LFP. Although it is considered very safe compared to other chemistries, uh, if you watch the news, you will continue, and we will still continue to see battery fires with LFP. There was one last year that shut down the 15 freeway, which is the freeway from Southern California to Vegas, and that prevented everyone from Southern California from coming to Vegas because of that battery fire. Um, and it was an LFP battery. So it can catch on fire. There are safeties you could put in place, but these fires do exist and it can happen. Um, Sodium and LTO, those are the two safer chemistries that are available today. It's much more difficult to get them into thermal runaway, and part of that is because it has lower energy density, so that's part of it. The other part of it is it's just the general chemistry. It's just a safer overall chemistry.
Um, why was EBOS invented?
Oh, so this is I think I mentioned this earlier that it was due to the chat is due to solving the light load issue that we run into in our industry. So this solves the light load issue and it also solves the wet stacking issue we have with our diesel generators.
All right. That's all the questions I see for now, but if you have any other, feel free to send them to me and I can forward them on to Michael. So thank you again, Michael and A&A, for hosting this afternoon's Power Talk webinar. It's very informative. And thank you all for joining us. We hope you have a good rest of your afternoon.
Great. Thanks, everybody.